Okay, let's get into this deep dive. Think back maybe to when you first learned about our solar system.
Right.
Chances are you pictured this, well, this neat lineup of 9 planets going around the sun. Maybe some asteroids, a comet swooshing by.
The classic picture, yeah. Very orderly.
But the reality we've uncovered now,
hmm
it's just breathtakingly complex and honestly beautiful.
Oh, absolutely. It's this magnificent, huge system, full of incredible chemistry, really mind-bending physics.
And still these fundamental questions about how it all came together.
Exactly. And what's really striking is how recently we figured some basic stuff out.
Like the sun's energy. We didn't really crack that code until, what, 1927? Nuclear fusion, that's less than 100 years ago.
It's amazing. And the
Mhm.
deep space missions are constantly sending back data that just adds more layers, more fascination.
So that simple, almost cartoonish view has really evolved.
Hugely. Especially as our telescopes and techniques got better. We now know about this sheer multitude of smaller things out there.
Right, not just the planets.
No, you've got asteroids whizzing about, those near-Earth ones that sometimes get a bit close for comfort.
Gives us a cosmic nudge, yeah.
Then there's the Kuiper Belt, just packed with icy bodies way out past Neptune. And even further, the Oort cloud comets.
And they're not just moving in simple paths, are they?
Not at all. It's this incredibly complex gravitational dance. They're constantly interacting, pulling on each other. It keeps surprising researchers, actually.
Absolutely. And then remember the 1990s, the discovery of planets orbiting other stars, exoplanets.
Oh, that was a game changer. Totally blew things open.
It wasn't just our solar system anymore. Suddenly, planetary systems seemed like, well, maybe the norm.
Exactly. And studying all those diverse systems really helped nail down the general model for how they form.
It's that classic story, isn't it? Big cloud of interstellar gas and dust.
Uh-huh. Collapses under its own gravity, starts spinning.
Ignites the star, our sun, right in the middle.
Yep. And then the planets slowly build up from all the leftover stuff swirling around in that disk.
With the heavier, rocky material staying closer in near the heat.
Right. And the lighter stuff, the gas and ice, forming the giants further out.
Makes sense.
But think about the next step. You've got this newly formed system, planets settling down, but there's still leftover debris. Asteroids, comets.
And lots of gravitational pushing and shoving going on.
Precisely. Think of it like cosmic billiards. Planets interact, smaller bodies get perturbed.
And some get flung out.
Some get flung into really stretched out elliptical orbits, but others, they get enough of a kick to be ejected entirely.
Ejected from their home star system.
Completely. Sent flying out into interstellar space as these, well, interstellar wanderers, traveling for millions, maybe billions of years.
Oh, so if our system did that, and presumably countless other star systems did too.
Then inevitably, some of those castaways from other systems should occasionally wander into our solar system.
Interstellar visitors. And they'd look different, wouldn't they? Orbit-wise.
That's the key. They wouldn't be bound by our sun's gravity like planets or our own comets. They'd be on what we call hyperbolic orbits.
Meaning they just fly through once and keep going? Not elliptical, like ours.
Exactly. Extremely hyperbolic. That's the telltale sign. And finding them, well, that's the challenge.
So people started looking.
Yeah, serious searches kicked off around 1990. The main technique is pretty straightforward, conceptually at least.
Making pictures.
Repeatedly, you image the same patch of sky over, say, days or weeks, and look for anything that's moved against the background stars.
Like spotting a tiny boat moving on a distant ocean?
Good analogy. Then you track that movement, get more observations, and eventually you can calculate its path, its orbit.
And it sounds like there were a few false alarms early on. Things that looked promising.
There were. The sources mention a couple of comets, C2007W1 and C1853E1. Initially, their orbits looked like they might be hyperbolic.
But they weren't.
Nope. Once astronomers got more precise measurements and refined the calculations, it turned out they were just members of our own Oort cloud on very long, stretched-out orbits, but still bound to the sun, almost RANs.
So why is it so hard? Is space just that big?
That's a huge part of it, the sheer emptiness. Early on, theorists tried to estimate, how many of these interstellar planetesimals might actually be floating around out there.
And the numbers weren't encouraging.
Pretty low, actually. Even assuming every star system ejects a decent amount of stuff during formation, the resulting density in interstellar space is just incredibly sparse.
So the chances of one passing close by are tiny.
Very small. The estimates suggested maybe a 1-kilometer-sized object might pass within 5 astronomical units of the sun. That's roughly Jupiter's distance, maybe only about once a year.
Once a year. That still sounds rare, but maybe not impossible.
But remember how faint they'd be. At 5.0, a kilometer-sized object is around magnitude 24.
Which is incredibly dim, like way beyond what you can see with your eye, needs powerful telescopes.
Exactly. You're searching for an incredibly faint, fast-moving needle in a colossal haystack. So for decades, it wasn't really surprising we hadn't found one. Even later models didn't drastically change that picture of rarity.
Okay, setting the stage for a surprise.
A huge one. October 2017, everything changed. The astronomy community was just buzzing.
What happened?
The announcement of the first confirmed interstellar object, discovered by the Pan-STARRS Survey Telescope in Hawaii.
And it got a name.
It did, a Hawaiian name. Oumuamua means something like scout or first distant messenger.
A scout from another star system. When did they find it?
About 40 days after it had already made its closest pass by the sun, so it was already heading back out.
Still close enough to see, though?
Just barely. It was within Mercury's orbit, but faint magnitude 22. And small, estimated maybe 100 meters across.
But the orbit. That's the clincher. Oh, yeah. Wildly hyperbolic. An eccentricity of 1.192. That's the highest ever seen for any object passing through.
Remind us what eccentricity means again. 0 is a circle. Right. 0 is a circle. Values up to 1 are increasingly stretched ellipses like our comets have. But above 1, that means it's not bound. It's on an open path. One pass and is gone forever.
Wow. And fast, too.
Incredibly fast. Its incoming velocity before the sun's gravity pulled on it was around 26 kilometers per second, just cruising through interstellar space at that speed.
So this discovery must have just set off a frenzy of research.
Oh, absolutely. Intense doesn't even begin to cover it. Within just 3 months, something like over 30 different groups were studying it.
Trying to figure out everything they could before it got too far away.
Exactly. Its orbit, trying to nail down its shape, how it was rotating, what its surface might be like.
And the shape was one of the biggest surprises, wasn't it?
Definitely. It wasn't your typical lumpy asteroid or roundish comet nucleus. The way its brightness varied as it tumbled suggested it was incredibly elongated.
Like a cigar.
Pretty much. Estimates ranged from maybe a 5-to-1 length to width ratio, maybe even 10-to-1, just remarkably stretched out.
How could something get that shape?
Well, a really interesting idea came up. Think about it traveling through interstellar space for maybe millions of years.
Okay.
It's not totally empty out there. There's very fine dust, like micron-sized grains. And Oumuamua is hitting these at high speed, 26 kilometers per second.
So, like cosmic sandblasting.
That's a great way to put it. Each impact is tiny, but over millions of years, countless impacts could effectively erode it, sculpt it, maybe preferentially along certain axes, leading to that elongated shape.
That's a wild thought.
Mhm.
Of course, with something so weird, people started speculating other things too, right?
Oh, inevitably. The alien idea definitely hit the headlines. Was it artificial?
Did astronomers check?
They did.
Yeah.
Radio telescopes were pointed at it, listening for any kind of artificial signal, any transmitter. Nothing, just background noise. So they could set upper limits on how powerful any transmitter could be, and it was very low.
There was even talk of trying to send a probe after it.
Yeah, some very preliminary thoughts about a flyby mission. But, I mean, it was already moving so fast, heading away from us. Launching something to catch it would have been technologically heroic, let's say. Extremely difficult.
Okay, so maybe not aliens. But where did it come from? Which star system?
Ah, that's the million-dollar question, and it's incredibly hard to answer.
Why? Can't you just trace its path backwards?
You can try, but think about the timescales. We're talking maybe millions of years of travel time.
Right, it was moving fast.
26 kilometers a second covers a huge distance over a million years, something like 25 parsecs, which is what, over 80 light years?
And stars aren't fixed, are they?
Exactly. Everything's moving. Our whole galactic neighborhood is dynamic. So you need to know not just Oumuamua's path, but the past positions and motions of potentially thousands of stars very accurately.
Which we don't always have. Especially looking back millions of years.
Precisely. Plus, Oumuamua wouldn't have traveled in a perfectly straight line. It would have felt subtle gravitational tugs from stars it passed relatively close to along the way.
So it's like trying to reconstruct the path of a leaf blown across a continent in shifting winds over centuries.
That's a pretty good analogy, yeah. But scientists did attempt it using the best data available.
How? What's the method?
Basically, you run its motion backward in time computationally, you factor in the overall gravity of the Milky Way galaxy, and then you try to account for the individual gravitational kicks from known stars it might have encountered.
So what did the early attempts find before we had the really precise Gaia data?
One of the first big studies looked at, I think, over 200,000 nearby stars. They crunched the numbers to see which ones Oumuamua might have passed close to.
Any likely candidates pop up?
They found about 109 stars it would have passed within about 3.5 parsecs, which is roughly 11 light years. Two encounters stood out as being much closer.
Which ones?
One was with a star called HIP 3757, about 118,000 years ago. Oumuamua would have passed just 0.04 parsecs away. That's really close, cosmically speaking.
Wow. Was that the origin then?
Probably not. The problem was the speed. The relative speed between Oumuamua and HIP 3757 during that encounter was calculated to be really high, like 50 to 100 kilometers per second.
Meaning it would have had to be ejected from that system at that crazy speed?
Exactly. Which seems unlikely based on how we think planets and planetesimals get ejected. Usually it's much lower speeds. Same issue with the other close-ish encounter they found with GJ 4274. High relative speed again.
So back to the drawing board. Did they look further?
They did. They expanded the search, looked deeper into that catalog of over 200,000 stars, maybe looking further back in time, and that yielded only 4 really promising candidates.
4 out of 200,000, that's narrowing it down.
Definitely. And their best bet, the most plausible one, was a star called HIP 113020. It's also known as GJ 876.
Anything special about that star?
Yeah, it's actually known to have planets, a system of 4 planets orbiting it.
Okay, that makes sense as a potential source. What was the encounter like?
It happened much longer ago, about 790,000 years. But the key thing was the relative velocity much lower, only about 3.9 kilometers per second.
That sounds much more reasonable for ejection event.
Way more plausible, yes. So that was looking like a strong contender based on that pre-Gaia data.
But then came Gaia. For listeners maybe not familiar, Gaia is this incredible ESA space mission that's mapping, like, billions of stars with insane precision.
Unprecedented precision, yeah. Positions,
Right.
motions, distances. It's revolutionized galactic astronomy.
So people redid the Oumuamua backtracking using Gaia data, specifically Data Release 2, or DR2.
Absolutely. And it refined the picture significantly. One major study using Gaia DR2 by Baylor Jones and colleagues took a fresh look.
What did they find? Did HIP 113020 hold up?
Interestingly, their analysis didn't favor HIP 113020 as strongly. Instead, they found that the closest encounter was actually with that same star from the earlier study, HIP 3757.
The one with the high relative velocity.
The very same. Their calculation put the encounter about 1 million years ago at a distance of 0.6 parsecs, but the relative velocity was still quite high, around 24.7 kilometers per second. Still a bit problematic as an origin.
So Gaia complicated things again. Did it find any better candidates?
They found another interesting possibility, a star called HD 292249. The encounter was further away, about 1.6 parsecs, and further back in time, 3.8 million years ago.
The velocity.
Lower, about 10.7 kilometers per second, more plausible than HIP 3757, perhaps. But beyond those two, they only found maybe 2 other stars with sort of intermediate characteristics, nothing screamingly obvious.
So even with Gaia's amazing data, we still don't have a definitive home address for Oumuamua.
That's the bottom line right now, yeah. It remains a mystery. We have some intriguing candidates. We understand the kinds of encounters it likely had, but pinpointing the specific star, it's still elusive.
But there's hope for the future. More Gaia data coming.
Definitely. Gaia is still operating, and future data releases like DR3 and beyond will provide even more accurate measurements for even more stars and track their motions over longer baselines.
Meaning we can run those backward calculations again with even better precision.
Exactly. Each new data release gives us a better shot at potentially tracing Oumuamua back to its interstellar doorstep. The story isn't over yet.
So what does this all mean for you listening right now?
Well, it's just a powerful reminder, isn't it, of the incredible scale, the constant motion, the dynamism of the cosmos.
It really is.
And it makes you wonder, I mean, given how many stars are out there, how many planetary systems are likely forming and evolving and, yes, ejecting material, just how many other Oumuamuas, how many other interstellar travelers might be silently zipping through our own solar system right now, completely unseen.
It's a mind-boggling thought. Billions upon billions of stars, likely trillions of these ejected objects wandering the galaxy.
And we just happened to catch one. Makes you think, what else is out there in our own cosmic backyard just waiting to be discovered?